Okay, so it's again this kind of circuit. You got a EMF and you got an internal and an external resistance. So first, let's talk about the terminal PD, which is basically the potential difference across the external load. So this terminal PD can be written as R out of R plus R of E. This is just the potential divider principle. The PD across the internal and the external resistance should add up to E. So the PD across the external resistor is a fraction of the total PD, and that fraction follows the potential divider principle. It follows the ratio of this guy's resistance divided by the total resistance. So from this formula alone, you can see that when R is 0, the terminal PD is 0, and when R approaches infinity, then the terminal PD approaches the EMF of the battery. And this should make sense, huh? Obviously, when you short the power supply, you're not going to get any terminal PD. But if you increase the resistance until effectively it's an open circuit, then you'll get the EMF of the battery. So as far as the terminal PD is concerned, it's quite simple. As long as you increase this resistance, the terminal PD will keep rising. Okay, what about the power dissipated in the external load? Okay, let's start from, if the external load is a 0 ohm resistor, then what is the power dissipated through it? Now, if you think in terms of I square R, so I is the current through this external load, and R is of course the resistance of the external load. When the external load has got 0 resistance, I is of course just E divided by R, because the internal resistance is the only resistance left. But this guy is 0. So the power dissipated in this external load is going to be 0. Okay? What if what will we think about the other extreme? If the external load has got infinite resistance. Now I would like to think of V square over R. So the power dissipated in this external load is the PD across this external load divided by its resistance. When this is an open circuit, the PD across this guy is basically just the EMF of the battery. But this guy is infinitely large. So again, the power will approach 0. So it looks like the variation of power dissipation in the external load is not so simple, huh? So as you increase the external load, the power dissipated in the load will start off as 0 when the external load is 0 ohms. So, and it will also end off approaching 0. So in between, there has got to be a peak somewhere. And it's to your advantage if you know this result, the so-called maximum power theorem, that this peak appears when the external resistance matches the internal resistance. So the peak power happens when external load is equals to R. So for this question, we were told that this external resistance is going to increase from 0 to 4R. So the power dissipated in the load is going to increase first before it decreases. Okay, so the maximum power theorem. It's not supposed to be in your syllabus, but still they set a question like this. So it's to your advantage if you know this. Alright, ta-ta!